Hi everyone. Today I'm going to present how to use graph neural operators to solve main-field game on graph, which models the interactions and optimal control among a large number of agents. Let's first look into one example of the game system, as shown in the figure. Many autonomous vehicles are running on traffic networks and aim to minimize their own travel cost. When the number of agents go to the infinity, the system can be captured by the decision-making of the representative agent. In this system, rho denotes the population density. The speed choice U and the route choice beta are the control of agents over the spatial temporal domain, and R is the cost. The control of this representative agent triggers the evolution of the system. To obtain the game equilibrium in this system is to solve a coupled forward-backward PDE. The forward equation is known as the FPK equation to capture the dynamics of the population evolution. The backward PDE is known as the HJB equation to capture the optimal control of the agent. As proved in our previous work, this coupled PDE system can also be reformulated into a populational MDP, as shown in the right figure. And we can use the state transition matrix as the information for the graph neural networks aggregation. To solve the coupled PDEs efficiently when the initial conditions vary, we propose a scalable learning framework using physics-informed graph neural operator called PICNO, because it can propagate information from initial conditions by projecting them into high-dimensional space. Our framework consists of two coupled modulus. The JNO modulus solves rho in the forward equations, and the HJB modulus solves optimal control U and beta. We now introduce two modulus separately. We first utilize a graph neural operator, JNO. We feed the neural operator with input fields ρ0, denoting the initial conditions. The input of the GNO is the initial population density, ρ0, along with the transition information to propagate population dynamics. The output of the GNO is the population dynamics over the spatial temporal domain, denoted by ρ0 to t. The GNO is initiated as the following MPNN. The cumulative message EIJKL indicates the ratio of population entering from edge KL to edge IG. The neighborhood message is transformed by a kernel function kappa phi and aggregated as an additional feature to estimated population density. The output of the GNO is then passed to the HGB module, which basically solves a Bellman equation regarding optimal control, given the rho. There are many numerical learning ways to solve the Bellman equation. In this work, we use backward induction, since the cost function form is known in the backward PDE. The output of the HGB modular U, beta, over the spatial temporal domain, along with the rho determined the residual to train the neural operator in the GNN modular. These two modulars internally depend on each other. Our scalable learning framework, PIGNO, can handle various initial population densities without recomputing mean field equilibriums. The initial distribution of autonomous vehicles along the route at time 0 is given. We sample ρ0 from the site consisting of various density distribution over the road network. Specifically, the right figure demonstrated the population density dynamics at mean field game equilibrium with along three passes. That is the path 1, 2, 3, 4, path 1, 2, 4, and path 1, 3, 4. The results obtained by the PICNO are consistent with the results solved separately using numerical method, showing that our framework offers a memory data efficient approach for solving the main field game on graph. Thanks for your watching.